All right, so I haven't actually graded all the homeworks yet, and I apologize about that. I'm going to try really hard to get everything graded today. So, especially a couple of you have some outstanding homework, so anything that's outstanding, I'm going to try to finish up today too. Um, so, hopefully, I'll finish up everything today. And um, yeah, oh, that's not right. It's not dark matter candidates. Let's fix that. That's what you get for. There you go. We'll talk about that today. So, today we'll go. Oh, really? Pardon me. Okay, bear with me 1 second. Okay, remember when I had. There you go. Okay. So. Okay, so long homework set. Covered a lot of stuff. My apologies for making it long. My planning abilities are not always where I need them to be. Um, but this is all the stuff that we were going to cover anyway, so all of these things were going to show up as a homework problem. It just would have been nicer if I split it into two. But okay, so let's see. Physical structures that give rise to the following aspects of an AGN spectrum. So what makes the radio continuum? Somebody yell something. Jets. What part of the jet? Synchrotron electrons. So the synchrotron radiation from hot electrons spinning around magnetic fields. Hot electrons are important. So when I'm answering this question, what I'm looking for is synchrotron and hot electrons. So the relativistic electrons spinning around magnetic fields, that's what gives us the radio. So I'll give you partial credit if all you say is jet. Can't tell how hot I am right now. The UV continuum, what makes the UV? The disk. So we've got that accretion disk, which is smashing stuff with gravity. That makes it hot. That makes it radiate. That makes all the photons come out. The broad lines? Yeah, it's little fluffy clouds at the end of the disk. And the narrow lines? So there's the stuff that's not orbiting. It's the stuff that's close to the black hole but not in orbit around it. It's the nearby gas. Okay, is everybody good with all of those things? So it's kind of a simple question for a really lot of physics. There's a lot of physics that's kind of behind each one of these questions. So when you're studying, make sure that you've got a familiarity with what each one of these things does and why. So why are they broad? Why are the broad lines broad? Doppler shift, because they're doing what? Orbiting what? The black hole, which is huge, so you can orbit it really fast. Yeah, okay. Observational zoology, list the observation. Oh, that's funny. That doesn't typeset correctly. This too should be up here. LaTeX doesn't always do what I want it to do. Anyway, list observational characteristics of these objects. So what's a QSO or a quasar? Tell me about it.
Quasi-stellar object.
Uh-huh.
And it could like outshine like all the total luminosity of the stars in a galaxy.
Right. High luminosity. Basically looks like a star, but it's way bright. Seifert 1. How do those compare to QSOs? It's all right there, so you can just read it. Less luminous than a QSO. Still pretty blue. Has broad lines. C for 2, same thing, no broad lines. Less luminous than a QSO. Why is it less luminous? Remember, there's this 2-parameter family.
Accretion rate and
The viewing angle.
the angle of viewing.
Accretion rate and viewing angle. So which one really gives you the total luminosity? The accretion rate. So how much it's feeding gives you how much light it gives you. How much it's feeding is proportional to its mass. So the accretion rate gives you a lot. BL lac. I didn't really spend a ton of time talking about them, but they're in the reading. What's a BL lac object, and why are they A, special, and B, how do we interpret what makes them weird?
Well, it's basically shooting the jet right at us.
Right. So that's why it's weird. What's weird about it?
Varying luminosity rate.
Right. The luminosity varies an enormous amount. There is no line radiation. All you see is the jet. Yeah.
If I remember correctly, like, you know that chart that has like type 2 and then type 1 and type 0?
Yeah.
And type 0 is unusual. Is this type 0?
A BL lac? No, this is so. I wouldn't worry too much about type 0. BL lac isn't one of those. I mean, this is a face-on galaxy, so the angle is right face-on, so we're looking right down the jet. So you see the whole velocity of the jet. And optically violent variables. What did you read about those?
Somewhat similar to a BL lac, but like shorter.
Right.
version.
It's in the optical
Optical
wavelength.
wavelengths. They're violent in the optical wavelengths, but not a lot of them are. And they have emission lines, whereas BL lac objects do not have emission lines. I'm not going to ask questions on the final that are a lot more detailed than that. The question might be, why do we only see one part of the spectrum in a BL lac? Why is that one part so much brighter? Yeah.
I heard there were like secret like 1.5s and like 1.9s.
Uh,
Was reading
yeah.
that on, like Wikipedia. Is that like actually a thing, or does nobody use that?
Well,
think it's in the book.
I don't really know.
Okay.
I can't really answer that question if it's really a thing, because there are some classifications that like somebody comes up with and writes a couple of papers on, but they don't have any teeth. Sometimes those classifications stick around. A lot of times those are like the internal workings of science, of like somebody writes a paper and says, oh, this is kind of between these things, I'm going to give it this designation. Astronomers are awful about doing that in a consistent way that makes sense. So I would ignore everything other than 1 and 2 as far as I'm concerned. If you're really getting into the details, then there's interesting physics there. Can I tell you one of my larger pet peeves? I'm not going to say biggest pet peeve about astronomy. That's magnitudes. So population 1. Okay, population 1 stars. I didn't spend a ton of time talking about population 1, 2, and 3. Population 1 stars have solar metallicities. So these are high metallicity stars. Population 2 stars, these are low metallicity. Why are they low metallicity? Why do they not have very much metal in the star themselves?
They're older.
Because they're older. They were born before there was a lot of metals. So this is like talking to your grandma who was born during the Depression, who grew up during the Depression. Actually, I don't think there are any grandmas left anymore that grew up during the Depression. Anyway, they were born in a time that was much more poor than now. So, your grandma that grew up during the Depression is a super penny pincher because she grew up with nothing. These things have low metallicity because they were born with nothing. It's about the birth, not so much about the old. So they were born early in the universe. So they don't have very much metals. So if I was going to go look for these objects, where would I look for the high Z population 1 stars?
A low resolution.
If I was looking in our galaxy, where would I look for the population 1 stars?
Any sort of star forming region?
Star forming regions, but where in the galaxy? So if I've got my galaxy that's got a halo, a disk, a bulge, a black hole in the center,
The disk.
which disk? Remember talking about the disk populations? So So there are several disk populations. There's a thin disk population and a thicker disk population. And the thicker disk population has the older metal poor stars. And then the halo has the really old metal poor stars. So you got this thin disk where the dust is, and that's where the stars form. And then they get kicked out and spread around into a thicker disk. And that's older stuff. And then the even older stuff gets kicked up into the halo. So all of this is stuff that I didn't cover as heavily this year as I normally do for whatever reason, but normally I spend a lot of time on this. Population 3, and I'm going somewhere funny with this too. Population 3 stars are 0. 0 metallicity. So these are the first stars in the universe. So in the early universe, there were no metals. Metals do all the cooling in the universe. And by metal, I mean everything bigger than helium. So carbon is a metal. No metals means what for the temperature of a cloud of gas?
Very
High, right? So no metals means it's hot. What does that mean for the gene's mass? Remember what the gene's mass does with temperature?
going to be very low.
It's
It's like
It's going to be larger because it goes like temperature to the 3 halves. So the gene's mass is very large. So these stars are massive. So the very first generation of stars we call population 3. They're massive and have no metals. Population 2 stars we have never observed. Now, if you see a press release that says first star in the universe observed, take it with a huge grain of salt. There are press releases that are starting to come out. People are starting to try to see these with JWST. Yeah.
Wait, population 3 or population 2 have never been observed?
Was that?
Which one? Okay.
3 has never been observed. There are a lot of these. They're in the galaxy, so we can see these guys. So now, okay, this bit, pay attention to and try to remember this because I might ask questions about this kind of thing on the final because it's in the book and we talked about it a little bit. Probably not a ton of questions, but remember this population 3, 2, 1 scenario. The annoying thing, which is the reason that I brought this up in the first place, is because after they started thinking about population 3 stars, then they were like, okay, what happens when you have one star that died? So you just have a little bit of metal. We're going to call that a population 3.5, which goes here, because fuck you.
3.5.
So anyway, I really hate the way astronomers name stuff. This is really where I'm coming with this. But also I wanted to talk about population 3, 2, and 1 stars because they're important for astronomy. Blah, 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 blah. Okay. Back to the homework. The main difference between Seifert 1 and Seifert 2 is the broad emission lines that are in Seifert 1s but not in Seifert 2s. So first, what's the interpretation of the structure that gives rise to these emission lines and why are they broad? Somebody holler.
Field region.
It's the broad line region. Where is it? What is it? We already answered this question, but let's do it again.
At the edge of the accretion disk.
Okay. Why are they broad?
High velocity.
High velocity. So they're orbiting like crazy because they're orbiting this giant object. And then in the unified picture, what's the cause for the difference in the spectra between 1 and 2? The viewing angle. Stuff in the way. Stuff in the way blocks the broad line region. That's hard to say. Is anything else I want to say about those? No. Oh wait, compute Eddington luminosity for Sag star. How do you do that?
Using the
I mean, there's just this formula. You just read it out. Right? So okay, the Eddington luminosity is this ratio of the proton mass and gravity and the Thomson cross section. Because remember, Eddington radiation is photons come out, hit all the electrons, push everything out. Okay, so they push on the electrons, and the electrons make an electric field and drag the protons with them. So the protons get dragged even though they don't do the pushing. So the effective mass of the proton mass is the dynamical mass. So photons push out, gravity pulls in. Those two things balance if the luminosity is high enough. They both go like 1/r squared, so they balance everywhere, which is important. If they went like if one of them went like 1/r cubed, then there'd be a point where one dominates and a point where the other dominates. And then you just make a big object. Here, either the luminosity wins or it doesn't. So 1.3 times 10 to the 38 solar mass m sun, so you should have gotten 5.2 times 10 to the 44 ergs per second. Good. And then, I'm not crazy about this problem. I don't like it, but we ran with it anyway. So if the stars are blowing 10 to the minus 4 solar masses per year in wind, which is not unreasonable for a bunch of big-ass stars, but totally high for what's actually going on in this, totally a fictitious number for what's going on in the galactic center. But if all the material is accreted, what is the efficiency given that Sagittarius star has a luminosity of 5 times 10 to the 36 ergs per second? This is right. That's actually the luminosity of Sagittarius star. So what do I mean by that? So what I'm... I want to leave that up. Leave that so you're looking at it. Where was I? Okay, so luminosity is an erg per second is some fraction of mc squared. M dot c squared. Because that makes it per time. mc squared is just the mass energy. M dot c squared is the mass energy rate. And epsilon is how much of it. And epsilon is like, I think you can get as big as like 0.8. So that can get pretty large. So if I say that, then I've given you the mass accretion rate as 10 to the minus 4 solar masses per year. And this is equal to the luminosity. So you just say that the efficiency is going to be the luminosity over the accretion rate, which I gave you, times c squared, which you can look up. And you should get a number of like, what did you guys get? Something like 10 to the minus 7. Yeah.
What's the physical property that determines efficiency?
I don't 100% know. That's part of why I hate this problem. Because I haven't sat down to go sort out actually what the efficiency of these things are and how much it varies. So this is kind of a fiction number. So it can't be 1 because that would mean annihilation of the objects completely, which black holes don't quite do. But they do give up a large fraction of the mass energy. So I'm not 100% sure what sets epsilon. Well, so some things set epsilon, like the accretion rate. So how does this? So I have this black hole, and I have this disk. Draw this one out. If I have something that's on this orbit here, what do I have to do to get it to go onto this orbit, this inner orbit here? What's that?
It's gonna like lose some energy.
Energy is easy to get rid of.
Angular momentum.
Angular momentum, however, is really hard to get rid of. So that's the thing that sets the ultimate efficiency of the accretion, is how quickly stuff can rain onto the disk and then get transported into the short shield radius, into the event horizon. This process is really not understood very well because these discs are spinning like crazy and really don't have very high viscosity. So the viscosity is how much, if I've got two streams of fluid and they're moving next to each other, one stream will make the other stream go faster and they will trade angular momentum. So they're trying to get to having the same momentum. That's what the viscosity does. It swaps momentum from here over to here and low momentum from here over to here so that it equilibrates. But the viscosity in these disks is really low. Too low to actually do the accretion that we need. So you have to invoke turbulence. And magnetic fields. And we will talk about those when we take hydro, but I'm not teaching hydro for at least 2 years. So it's very cool stuff. So it's turbulence and messy, but turbulence is beyond what we want to talk about in this class because it's a mess. Okay, any other questions on Eddington accretion? Okay, so from Eddington accretion, you can get a luminosity, you can get a mass, you can get an accretion rate. All of these three things are related. So how bright the thing is, how hard it's feeding, and how big it is are all tightly related. One particular problem that I might ask, let's just take a brief aside. I'll talk. So I'm going through. There it is. That says L Eddington. So the luminosity is some fraction. We'll call this, say, like 0.75 or something like that. Maybe I'll call it 0.1. If I'm giving you a problem, I will give you some reasonable number for this. M dot, C is a number, L is a number, M is a number, M. Here, let's make this less confusing. Now they're both capital. They're both the same M. One equation, one thing that I might ask you is give me an evolution equation for the mass. Do you see how to do that? This is a differential equation. This is dm dt times epsilon c squared, just numbers, equals L Eddington over solar masses times m. Now, do you see how to make an evolution equation for, I want mass versus time? There's several ways to do it. Really what I want you to know is just to be able to write down the answer. How do you write down the answer? This is an exponential. This is dm dt is something times m. A thing that when its time derivative depends on the thing, then you get an exponential. So m of t is m naught. Let's call it m1 so that it doesn't look like a solar mass. That's your initial mass. That comes from the boundary condition. E to the, what do we have? L Eddington over epsilon c squared, solar masses, times time. See all that? Or I could just call this m dot, but that's okay. So the growth should be exponential in time. This is the kind of problem that I wouldn't feel bad putting on the test, because I think that everybody should be able to solve this differential equation. df dt equals a times f. F equals f naught e to the at. If you can do it every time, if you can go through the derivation every time, you can split this guy over here and this goes over here. You integrate, you get a log, you exponentiate, you're done. You don't have to go through that every time. Just remember the answer. I'm not telling you to memorize basically anything other than this. Just learn how this works. Memorize it for now, rederive it every time you need to, but make sure that this kind of differential equation is fresh in your brain, because I don't feel bad putting it on the test. Okay. Do I have anything else that I want to say about Eddington? No, I don't think so. Let's talk about reverberation mapping, because I like reverberation mapping. I'm not sure why I find reverberation mapping super interesting and entertaining. A lot of it is because it's this huge object that's just vibrating, and you're just watching these enormous, like the biggest objects in the world or in the universe, vibrating like crazy. We'll leave this one. Over here. Oh, that's another one. Here's another problem. When I get to it, I have another problem that I might assign for the final that I'm going to tell you about. I haven't written the final yet, so I don't feel bad about telling you the ideas that I might have about final problems. But where are we? Okay, reverberation mapping. Let's talk about reverberation mapping. So I see two signals. I see a continuum spectrum in the ultraviolet, and I see line emission from carbon-3. Which one occurs first in time and why? Yeah.
The continuum comes first because the line has to wait for the light to travel from the disk to the broadline region and ionize the broadline region to give off the line emission.
Everybody follow that? Everybody good? So I have my black hole. Now it's a red hole. I have my inner disk. I have my little fluffy clouds. Remember from the second problem, the first problem, right? The UV comes from the inner disk. The broad line emission comes from the broad line region way out here. The reason the broad line emission gives us lines is because the UV pumps the lines. This is fluorescence, just like a fluorescent marker. So if you have a fluorescent marker, why does it look real bright? Because the UV photons hit it, excite a thing, and then it falls back down. So just like here. UV photons come off of here, have to travel, and it takes them some time to travel. That travel time is not instantaneous. This might be a month, or several days, or a couple of weeks, so it might be a while. So this one goes first, and then that one happens. Then second, the lag between the two is seen to be 30 days. The width of the broad line region is 2,500 kilometers a second. Assuming the simplest thing possible, what do I ask? What's the distance from the BLR to the central black hole? And leave it in parsecs. So how do I do that? I'll leave that with you. How do I do that? I want this distance here. D is what?
C times T.
Yeah.
D is C times T. Oh, I have T, right? I gave you T. So this is 30 days times 24 hours times 3,600 seconds times, that's it, times C, which is 1, or in the units that you want. Leave it in parsecs. Oh man, I should know what C is in parsecs. Anyway. So we get, what did I get? 0.2 parsecs. Everything there? And the next question is, what's the mass of the black hole? I wouldn't feel bad about not asking the second question and just saying, given that the lag is 23.5 days and the broadline region width is 1,500 kilometers a second, what's the mass of the black hole? That's all you need is a time, you need a clock, and you need that velocity. And then you get the mass of the black hole. Now, okay, to do it actually, if you're going to write a paper, you got to be a little bit more careful with the geometry, but I don't care about it at this point. It's just a couple extra intervals. So what's the black hole mass? I have D How do I get the mass?
Zero.
Barrel theorem. D squared equals gm over d. So m equals 2,500 kilometers per second over 2 squared. Why over 2? Because when I have a spectrum, if this is a spectrum, this is a velocity. This side is the stuff that's coming towards me, and this side is the stuff that's going away from me. So I want just half of that. I just want one of them. So the width gives you the difference of coming towards and going away, which is half of the velocity that you want. I'm not going to take off very many points if you mess that up. That divided by g, which is 1 over 233 in units that you feel like dealing with. D in parsecs. Then 1 over 233 will give you an answer in solar masses. You use d in parsecs and this in kilometers per second squared, which is why we use g that way. And what do you get? What do you guys get? Yeah, I get 9 times 10 to the 6. So if you got, 1 point something times 10 to the 7, that's reasonable because you're off by a factor of square root of 2. Everybody good? Make sure you can do this. That's a hint. Mortlock quasar is one of the highest redshift objects ever discovered. Oh man, I like doing astronomy right now because all of the stuff that I say is out of date. And this is out of date because now we have all of these galaxies at like redshift 13, which is bonkers to me. It's really cool.
I was a little confused. I'm like, 7, isn't that a little like low? We've had stuff.
It is now.
I remember seeing 13.
But it wasn't in October.
Wow.
All the data got released in October. So in October, this is a perfectly fine sentence, but now we have all these other objects. So its luminosity is 6 times 10 to the 13 solar luminosities. What is its mass? And I took this from the abstract of the Discovery paper. So what you're doing here is exactly what they did when they found the thing and reported its mass in the first place. So how do we find its mass? Eddington. So we just divide by that 1.38 times 10 to the 38 ergs per second. And I didn't write it here, but what do you get?
2.1 times 10 to the 9.
Is you get 2 times 10 to the 9. Think about 2 times 10 to the 9 solar masses. That's a god-awful amount of mass. This is exponential, which is pretty fast. But if this is too large, we probably still have a problem. One of the problems that I didn't leave for a homework but might show up on the final is if an object is accreting at Eddington for the entire duration of the universe, how big can it get by a redshift of 7? I'll soft pad the problem a little bit more. But that basic idea of I've got a black hole that's going to accrete at Eddington for the entire duration of the universe, how big can it get? Depends on 2 things. It depends on the initial seed mass, M1, and it depends on the amount that it's accreting, M dot. Even if you start with M1 reasonable, you still can't get big enough black holes, which is weird. Okay, so how much smaller was the universe at this time? 8 times smaller. Okay. How are we on time? We're fine on time. Okay, compute the virial radius and virial mass for a cluster that has a density profile of rho goes like sigma squared over 2 pi g r squared. And sigma here is 300 kilometers a second. So how do we do that? How do we find the virial radius? You have to find that first.
When the density is 200 times the critical density.
That's right. So this is rho of r. This is rho. Goes like some number over 2 pi g. That's just a number. R squared. I set it to 300 kilometers a second because that's a reasonable number. And what we want to do is find out when the density is 200. So we say that 200 rho c equals sigma squared over 2 pi g r squared. And the notes, I realized as I was in office hours yesterday that in the solutions, if these solutions aren't up, shoot me an email. I think I posted them, but I can't remember if I posted the solutions to this homework set or not. I would have done it just like a minute ago, but I think I forgot. They're not there? Okay. If they're not up by the end of the day, somebody shoot me an email. I'm going to try to remember. But I want to make sure that everything is up now so that you can start studying. And the answer is I did the math. So you'll see here, this is a little different. This is 3 sigma squared instead of 2 pi, 1 over 2 pi. Not a huge difference, but it gives you a slightly different answer. So my answer here is going to be a little different than yours because I was an idiot when I was computing the solutions. You should always write the solution to the problem when you write the problem. You really should. And if you don't, then you get inconsistencies. So, okay. We want this radius, so we just solve and we get that r should be like r comes over here, this goes over there, sigma squared over 2 pi g times 200 rho c. Square root of all of that business. And it's most useful if you do this in parsecs, and you should get something that's like 1 megaparsec, or 0.3 megaparsecs, or 300,000 light years, or 300,000 parsecs, or a million light years. So anyway, so you should get a number that's on the order of 1 megaparsec. I got 1.6, but I think it's high. I don't like that number, so I'm going to downscale that. It's the right ballpark, though. Does that make sense to everybody, how I got here? And then the virial mass is just what's the volume of a sphere?
453 times density times r.
Right, so 4/3 pi r cubed is the volume of a sphere times the density gives you the mass. That's all you need to do. Like, really, it's a dumb thing. You could do an integral too, but you get the same answer. So you should get a mass of on the order of 10 to the 14 solar masses. It's a big object. Okay. Anybody have any questions about this one? Largely makes sense. Okay, R500. This is the same idea, just rho 500 is 500 times rho c. So the 200 comes from some math you can do. It's a cartoon. It's not based on any like real physics. It's based on some cartoon that you can write down, which I can show you, but I'm not gonna. This is basically if I just take a thing in an expanding universe and I let it collapse, what's it do? It turns into an object that has a radius of about 200, or a density of about 200. But clearly that's not the edge of the object. The edge of the object is way out there. So R500 is just another kind of fiducial mass that people can use. So first, define R vir. The reason that I ask you to define R vir is sometimes I assign this problem without doing the other one, and so I want to put whatever the virial radius is in people's heads. So whatever you put there, you're probably going to get points for. The second bit is compute R500 over R vir, assuming the cluster has a 1 over R squared density profile. So if rho goes like R to the minus 2, then 500 times rho c over 200 times rho c is going to be, all this is going to cancel, and we're just going to be left with R500 to the minus 2 over R200 to the minus 2. So all that cancels and all this cancels, so this is just 5 halves. Is the ratio squared, so R500 to R virial, or R200, is going to be the square root of 2/5. Just got to flip that over and, oh wait. Yeah, no, that's right, 2/5. the minus sign up here. You gotta flip it over, take a square root. Are we good? And then compute M500 to M virial. The easiest way to do this is just to notice that the mass goes like the radius. This is one of the chief problems with 1 over r squared, because the mass increases without bound. That doesn't make any sense from an object that needs to have an edge. But if you just know that m goes like r, then m virial over 500 is just the square root of 500 over 200. And then the next thing, the reason that I gave this problem at all is because a lot of the scaling relationships are relative to M500 that are in the book, and I don't feel like recomputing everything. We'll just be consistent with what the literature says. So given a cluster that has an X-ray temperature of 10 to the 7, what do you expect its virial mass to be? So there's this relationship. Virial, in the book, it's M500 is what the relationship is about. And it's in that section. It's just in a line of text. And you get a number, it's square root of 2/5 smaller than this. So I had the square root of 5 over 2 is because I'm asking for the virial mass, not the M500. So you should get about 4 times 10 to the 13. Are you happy with that? You feel good? And then what should the velocity of dispersion of galaxies be, assuming it's virialized? You just use, again, sigma squared equals gm over r. And you get 315. So m is 4 pi. Why did I do it that way? Oh, I need arbor. That's why. Because you need the virial radius, which you just get. And then you plug it in. So you need to get the virial radius first, and then you get the virial everything. Are we good? All right. Almost done. 2 more left. Okay, we had talked about radial segregation of galaxies. So this plot, actually, I'm going to fire up. Lecture for today. Where'd it go? Why are you not loading? There you go. Big old jet. Until they finish downloading. What are you downloading from? Doesn't make any sense. Not on the cloud, ball. There you are. So these plots, yeah.
Are you gonna post these slides too?
They should be up. They should be there now. And again, if they're not there now, I'm going to go through all the files and make sure everything. But if they're not by the end of the day, shoot me an email. So these 2 plots show us the distributions of various galaxy types within galaxy clusters as a function of density and as a function of position. So which matters more, density or position? So things get denser as you get towards the center. So what this shows is that if we look at the early type galaxies tend to be concentrated towards the center of the cluster, and late type galaxies tend to be concentrated towards the edge of the cluster. This is a running theme. So is it because the density is high and all of the high density galaxies all turn into the high density spiral galaxies turn into into red galaxies? Or are we just shifting everything around? Are we actually changing the population of galaxies, or are we just moving them so that the red ones are in the middle and the blue ones are on the outside? That's the question. Is the galaxy population actually changing? And Butcher-Omler isn't here. Oh man. So what Butcher-Omler shows is that the fraction of blue spirals increases with redshift. So that says that the galaxy populations are actually changing. Does that make sense? So Butcher-Omo shows that the total fraction of blue galaxies increases with redshift. So that means going back in time, things get bluer. So that means this radial distribution within galaxy clusters comes from the evolution of the galaxies. As galaxies turn into redder galaxies because they smash into each other and they burn out. Okay, describe SZ effect. So what is Sunyaev-Zoldovich? Somebody yell.
Inverse Compton effect of hot electrons hitting photons from the CMB.
Exactly. And what does that do to the observation of that galaxy cluster?
Makes it easier, right?
Well, it makes it look
You can
hotter.
measure the distance.
Well, you can measure the distance, but just the observation, it makes it look like a hot spot in the CMB because it makes
Right.
those photons look a little bit hotter. So if I'm looking at the CMB and I look for hot spots, or if I'm looking at longer wavelength cold spots because those photons got shifted, I look for regions where the photon distribution is to a higher energy photons. Then demonstrate that you can use it to get the distance to a cluster. What things do you need to measure? So the first thing you need to know is that the total intensity shift is proportional to the density, the size of the cloud, and its temperature. So this is that shift y, this y parameter. And they write it down as an integral, but every integral over space you can just turn into, you just assume everything's constant on the inside of the integral and just multiply by the length. That's a cheap-ass way to do an integral. So an integral looks like this. Integral of q of x dx from 0 to L. That's just equal to q times L, as long as q is reasonably constant within that integral. Okay, it never is. We're going to do it anyway, because that's how astronomy works. So this really should be an integral, but we can't do that, so we just have the average density, the average length, and the temperature. So from the Bremsstrahlung, the Bremsstrahlung is proportional to the electron density squared, not just the electron density, like Sunyaev-Zoldovich is. So the X-ray intensity is the X-ray luminosity times the density squared. So we'll use this to get rid of this density, and we get a solution that gives us the shift of the CMB spectrum. It's proportional to the X-ray luminosity times the length times the temperature. So we need to measure the temperature, and we get that the distance is just the length over the angular diameter. So you need the angular diameter. It's just going to be the shift over the X-ray luminosity, which is kind of magnificent because what you're looking at is the shift in the microwave and the total brightness in the X-ray, and it gives you the distance to the object. It's kind of magic. Let's see, last one. Why is X-ray gas a better method for detecting galaxy clusters than optical groupings of clusters?
Get a 3D picture.
You get a better 3D picture.
You get a with the optical. They all look like they're in the same plane.
Right.
Actually proportional to the density squared.
X-rays are proportional to density squared, so that they're a more sensitive thing. So it gives you some of that 3D spectrum as well.
It shows borders.
Yeah, it'll show you, and it shows you the edge of the cluster where the X-ray luminosity disappears, and that's again the reason is because it's proportional to the density squared. So it's a really tight thermostat. So as the density goes up, suddenly you get a lot of X-ray luminosity. And how long did each of these take you? I recognize that it was like your entire Saturday for some of you. So I was impressed by the people who did it in like 4 hours. So, and of course, I take all those numbers with a grain of salt, and I don't actually judge anybody by them. But it's a really useful metric for me to know how badly I'm smacking you. Okay, does anybody have any questions about the homework? Yeah.
Could you define Sunyaev-Zoldovich condition?
Yeah. So SZ is process where I have a galaxy cluster and it sees, so here's me. There's me. Here's the CMB. There's gamma ray. Here's a big old cluster of gas. This is X-ray gas. Being X-ray gas, it's 10 to the 7 Kelvin. It's really hot. That means I have these 10 to the 7 Kelvin electrons. And this electron sees this CMB. Maybe the CMB photon comes in from over here. I mean, the CMB is over here too. The CMB is everywhere. It fills space. I drew it back here, but that's really not how it is. The CMB is everywhere. So a CMB photon comes up here and hits this hot electron and comes out as a slightly hotter photon. So there's an inverse Compton as the electron gives energy to the photon. Make sense? So that gives us, if this is the black body that is the CMB, so remember the CMB is this magnificent black body. In this spot of the sky, my black body will be shifted to a higher temperature black body. So the number of photons that I see at this wavelength will be decreased, and the number of photons I see at this wavelength will be increased. So this is like 80 gigahertz, and this is like 110 gigahertz. Does that make sense? So you can get distances because the shift in the intensity relative to the black body is equal to this parameter y, and it's minus 2y, but that doesn't matter. What it matters is it's proportional to the density of electrons, the length of the cloud, and the temperature of the electrons. So how likely is one of these CMB photons to hit an electron? It probably depends on the density of CMB photons too, but that's fixed. The density of electrons is the thing that can change with the galaxy cluster. So it's one factor of the electrons. The total size from here to here, because we're looking at the entire integral of the shift along the length of the cloud, and the temperature, that's how hot the electrons are. How much energy does one electron have? So the Siniozov-Dovich shift goes like the electron density, the size of the object, and the temperature. That's an important kind of collection of things. So then the other bit with that last problem, the total X-ray luminosity is going to go like the density of electrons squared times some stuff. So I can use this to get rid of this density of electrons because that's the hard part. 3D density is very, very, very difficult to measure. But I have this nice sensitive probe of the 3D density. So I'll use that, get rid of the density, and then I'm sorting. Because then I know everything. So the X-ray emission I can measure, the Siniozov-Dovich shift I can measure, electron temperature is impossible to measure, size of the cloud is very difficult to measure, temperature is easy to measure because I got the X-rays. So the temperature is easy, it's like 10 million Kelvin. The size is then what we can get from that. And then it's just a little bit of algebra. Make sense? Okay, let's go back to this. Okay, so what a prep. Chapters 1 through 6. I didn't really spend any time on chapter 1, but you should probably read it because it's I'm sorry, I think I had that shirt when I was a kid. Or something super like it. I'm looking at your shirt, I'm like, it's like triggering really old early memories. Sorry, the squirrel brain interrupts. Okay, so the first 6 chapters, don't read the lensing bits because I'm not covering lensing. No lensing will be on the final. 1 8.5 by 11, both sides, bring a calculator. All the plots and tables in the text. So spend a minute, flip through the text, look at each one of the plots. Make sure that, really importantly, look at all the tables, because there's a bunch of tables, especially in the galaxy section, where he outlines what are the masses of galaxies, what are the sizes of galaxies, what are the sizes of various things. So there are tables that get you like raw numbers that are useful. All the lecture slides, and I'm actually going to invert this. Might not be reflected. I want to do this in the opposite order. Homework first. Homework first. Because that's the bits that I think that you put your hands on. Those are the things that I think that I know that you can do. Okay, so let's give a kind of quick shorty tour. The final's at 10 on Monday here. Don't be late. Almost nobody's ever late, but from time to time. Okay, I did not spend, I was going to delete this slide. I didn't spend any time on this. So, okay, chapter 6. So this is going to be, we're going to start with the new stuff. The final is cumulative. So I'll ask stuff from the first half too. But I'll start with the new stuff since the midterm. So we talked about galaxy clusters. So we talked about the Abel catalog. We talked about distributions. We spent a lot of time with the isothermal sphere, 1 over r squared. We also talked about the King distribution, and I think we talked about the NFW distribution, but I don't think a ton. We talked about relaxation methods. We talked about two-body relaxation and violent relaxation. Violent relaxation was earlier in the semester, but the physics is still here and relevant and matters. Did I ramble to you guys about trying to get ChatGPT to... All right. Yeah, so the shorty answer, I asked ChatGPT about violent relaxation, and it gave me some papers that I really wanted to read that were complete fictions. It gave me citations that I should have seen, and I was like, what the hell? I should have seen this paper. I know all these people, and it's the topic that I want to... But it was a completely made-up paper. It gave me links and everything, but it didn't exist. So anyway, you can't trust ChatGPT for anything. It is not a trustworthy device. It'll make your text sound nice, so that's cool. That's what it can do.
Did you learn that from South Park?
No.
There's this episode that was actually, they used ChatGPT to create it.
Oh, did they really?
And the first thing they did in the episode was they used it to like text their girlfriends, and the girlfriends were like, "Oh, he's so sweet. He writes to me so well." Yeah, so that's what I thought about the text when they said that.
That's very funny. Yeah, galaxy Viridian theorem, mass radius. So if I ask you any of those mass radius relationships, I will give you the exponents and stuff. Unless the argument is explain how mass and temperature should be related. So that might be on there. Not high likelihood. Galaxy types, know that plot there. And Butcher-Elmore, which we just did. We talked about the X-ray radiation. We talked a bunch about the X-ray radiation. So make sure that you're comfortable with how Bremsstrahlung works and what it is and what that spectrum looks like. It's all in the book in better detail than what I did in class. Know how that that X-ray gas varies with mass. Know about the dark matter dynamics. I didn't spend any class time on the isothermal beta model. But what it says is if you assume that it's just gas, you get the wrong answer. So there has to be dark matter. Know what the bullet cluster means. One possible question would be I present a picture of the bullet cluster and ask you to describe which aspects of that image tell us that there's dark matter and what properties of dark matter can we see from that. Actually, let me pull that up real quick. Let's talk about that one. Where do I have it easiest? I think it's in the dark matter candidates page. It's not in here. What am I doing? It's in That one? No. Must be in cluster 3. There you go. The bullet cluster and the mass cluster. Here you go. Let's focus on this one. This is just, I was pointing at this thing. It doesn't mean anything about the connection between these two pictures. This is just crap left over from the pandemic, this arrow. So this guy. So what's the blue? Right. So the blue is the microlensing mass estimate. That's where the stuff is. And what's the pink? It's the X-ray gas. What happened? Yeah, 2 galaxy clusters. They passed through each other. The gas can't pass through the gas because it has pressure, so it shocks. But the dark matter and the galaxies can pass through each other because they take up no space. The dark matter doesn't see the dark matter. Yeah.
So, kind of 2 questions. So if it doesn't feel pressure, then what's stopping it from just all collapsing in? Is that like some kind of...
Oh man, it's almost always written up somewhere.
Is it the...
Right here. I'll just write it here. I don't use this board very often.
So it's moving... Like that.
So that's kinetic energy.
Yeah. Wait, let me read.
You know, I'll still be here. But that's a really important question. Galaxies don't stay up because of pressure. They stay up because this stuff is whipping around like crazy. Is there another hand? Yeah.
That's me, but you guys play.
Okay.
Yeah.
Okay, bullet cluster. Learn about the Sunyaev-Zeldovich effect. We heat up hot electrons heat up the sea of B photons, which is really cool. Be familiar with the scaling relationships. There's only a couple: mass temperature, mass dispersion, mass luminosity. And there's 2 of those. There's an X-ray luminosity and an infrared luminosity. So be familiar with those and what they are. Anything else that I want to know? Do you have any other questions about clusters right now? Giant balls of dark matter. That's what a cluster is. A galaxy cluster has nothing to do with galaxies. It has to do with the dark matter there. But there's galaxies in them, so you can learn stuff about the galaxies, and they're cool. Yeah.
I was just gonna ask a general question. If the intercluster medium is so hot, why is the interstellar medium in galaxies such a different temperature?
That's a great question. I will leave that as an open question to everybody. So we got the interstellar medium in a galaxy has a temperature of on the order of 10 to the 4 Kelvin, kind of typically. The intercluster medium has a temperature of 10 million Kelvin. So what sets the cluster temperature? No. The black holes are really small. The galaxy cluster doesn't care about the black holes. The dark matter, by way of V squared equals GM over R. For this huge virialized blob with a lot of temperature, the temperature is providing pressure on the gas. That makes sense? And they have a, yeah. Oh, we're running low on time. Cosmology. Cosmology was on the previous example, previous exam, but will be on this one as well. So, homogeneous isotropic expansion. I saw the coolest talk this morning where he talked about how it's not really homogeneous. Find that very satisfying. Radiation era, matter era, curvature era, which you can ignore. Dark energy era. Make sure you're familiar with those eras of the expansion, how we see them in math. How radius, mass, curvature evolve with radiation, mass, and dark energy evolve with scale factor. how A evolves with time in various eras, redshift scale factor relationship, these omegas. Why is it omega? What is this critical density? What's the closure density? Make sure you know the Friedman equation. That a squared equals h naught squared omega or radiation a to the fourth. Write that down. Make sure you understand the Einstein de Sitter model. Even though it's wrong, it's still real useful. Thermal history of the universe. You form all the protons, and then all the neutrinos, and then all the neutrons, and then the electrons, and then the dark matter's got to form in there somewhere, but we don't know where. Temperature evolution with time. Temperature evolves like A. 1 over A, and recombination. Dark matter candidates. So there's a whole lecture on dark matter candidates, and what I really want you to be familiar with is what are the important ones. Machos, axions, WIMPs, maybe neutrinos. Which ones have been absolutely ruled out? Neutrinos and machos. Which ones we're still looking for? WIMPs and axions. Which ones we think it probably is? I'm not going to ask you that question because I don't know anymore. I used to have an idea, but I've given up on that idea. Also, be familiar with how we detect how we are looking for them. So we have direct detection, indirect detection, and colliders. So this is actually seeing it. This is seeing it somewhere else, and this is making it. Numbers. You should know what the mass of a spiral galaxy is. High probability that one of the questions is, what's the typical mass of a Milky Way sized galaxy? I'll be asking for the dynamical mass because that's the thing that's easier to measure. But get your head around how big a CD galaxy is, how big a dwarf galaxy is, how big the Milky Way is, how big the size is, what's the size, what's the radius of the Milky Way? Does anybody know off the top of your head?
100,000 light years?
The diameter is about 100,000 light years. The radius is like 25, 30 kiloparsecs. Yeah.
For these numbers, you share what the number is, or do you
No,
know
Ed. Just like look at the table. This is part of, go back and look through all the tables. Just be familiar with it. So if I say how big is a CD galaxy, I don't want you to say 2 solar masses. I want you to say like between 10 to the 12 and 10 to the 15, somewhere in there. So if I ask how big is a galaxy, there will be a wide error bar on your answer, but you should basically know how big a galaxy is. This is like 30 seconds of work. It's not a lot. But it's one of those things that you forget. Like I forget to be helping you guys think logarithmically. Think about really large numbers and how they relate to really small numbers. You got to think everything is in the exponent. Age of the universe, the omegas, the closure density in solar masses per cubic megaparsec. I'll actually give you that if you need it. I'm not going to make you memorize that, but have a familiarity with the rest of these numbers. So, running themes. What can you do with the virial theorem? All kinds of stuff. Different methods for relaxation. A couple of those. Signatures of dark matter. So think about where do we see dark matter? How to learn about black holes. What color can tell you. We learned about star formation versus galactic properties. So how does a star formation history tell you about the galaxy that you observe? We talked about the distance ladder. We talked about galaxy evolution. How things change with the expansion. So density goes down like A cubed. Temperature goes down like A. Dark energy doesn't go down. We didn't do how things collapse. We'll learn about the possible dark matter candidates. This slide. Why dark matter? What rules out various kinds of dark matter? And now I'm over time. How to measure masses. There's a slide, a pair of slides on Canvas in the files that is a big list of how to measure masses and a big list of how to measure distances. Make sure you're familiar with everything on that pair of slides. It's this slide, and then there's another slide that talks about distances. So use that as a study guide. Ellipticals are violent. Distance ladder is important. It's basically this slide and the previous slide. Be familiar with these plots. I'm not going to talk about them right now because I'm actually over time. But be familiar with these ones. I like them. This plot. You're familiar with this plot? What these guys do, you should know how to do reverb mapping, at least in this cheap way that we did it on the homework. Understand these things. This plot tells us that we're all gonna die in a very boring way. It also won a guy a Nobel Prize. 3 people. And here's a jet. Okay, that's a whirlwind of everything that I think is in the class. Does anybody have any final questions? I don't know. You got 2 hours, so I'm gonna make it be basically what I think you guys can get done in like an hour and a half. And then I'm a terrible judge, so it'll probably be. So I have a pretty good idea of how long things take, you guys. That's why I ask. So 6, maybe 8. Probably not 8. Not 12. Maybe 6. But they be 6 of the simpler ones.
It's Monday at 10.
Monday at 10 in here.
I just realized I forgot to put how long each question is on my homework.
Oh, I haven't started grading yet, so just put it in the comments on Canvas. If you just stick it in the comments there, that's the easiest place to stick it.
Okay.
Yeah.
Also, what is the closure density again?
Okay, so it is. Okay, I can measure the mass of the Earth by throwing this up faster and faster. Oh, fart.
Oh.
That's okay. I'm done teaching it here. I don't need that anymore. The closure density is the universe had a big explosion. It's the mass that's necessary to make it collapse back on itself. It's the smallest mass, and it's not the mass, it's the mass density. So it's the mass density of the universe that's just big enough to make it collapse on itself.
Okay. Alright, thank you.
Yeah.
Oh, did you want to?
Not done.
Yeah.
Okay, just letting you know that I've been working on the paper homework.
Okay, great.
So I apologize on the lateness.
Okay. Get with me by end of the day tomorrow.
Today.
End of the day today would be better.
Yeah, I'm gonna try to shoot for today.
That would be
Yeah.
great, because then I can probably get a chance to look at them. If you get them to me by the end of tomorrow, then I'm probably not going to look at them before the exam.
Yeah,
Oh, neat. Oops.